right, so we'll start again with the second talk of this session, where it's my pleasure to introduce Tim Ortel, who will talk to us about minimal support for lattices and semigroups.
Great, thank you very much for the invitation, and thanks for the introduction. So, fittingly for the workshop, I will try to address like all the four keywords of the workshop. So, obviously, I'm going to talk about lattices. I'll try to apply some geometry, and I'll talk about some algorithmic aspects, and just to tick the last box, I'll pose an open hardness question, just to have everything there. So the things I want to talk about today is joint work with Iskander Aliyev, also from Cardiff, Gennady Avakov, he's now at BTU Cottbus, and Jesus de Loera from UC Davis. So the problem I want to look at is the integer feasibility problem in standard form. So I assume I have some linear constraints, ax equals b, and then I'm just going to add some positivity constraints, and my question is whether we can find, the finding part is actually not the important part, but I'm interested in an integer solution to this problem, and then in particular, I want to ask the question whether we can find actually solutions where the support is not too large. So by that I mean, can we say anything about solutions to an integer feasibility program on the number of non-zero components? To make my life a little easier, I'm not going to address at all the problem of actually finding the solution and whether it's feasible. So usually I'll just actually assume that the B is of such kind that the problem has actually some integer solution. And then secondly, I'm going to assume that the GCD of all the minors of my matrix A is equal to 1. This is mainly to make my life easier, and maybe yours a little bit as well, but it's actually not a big assumption. Essentially what I'm just saying is that if I look at all integer combinations of the columns of A, they just span the letters Zm, or alternatively, the Hermite-Normal form, for example, is just the identity of this matrix. And if this would not be if this condition would not hold, I would just actually divide everywhere by the GCD of the matrix A. Maybe there's some among you that don't like integer programming. Not a problem. You can just reformulate this problem a little bit and consider it as follows. Just consider the matrix A as a set of n columns. And then we just consider the semigroup, which is generated by all positive combinations of these columns. Then obviously, I'm interested in elements in the semigroup. That would be in this setting our B. And then the question is, what is the minimum number of elements, like from the generators, do I need actually to generate the element B? And then there's no integer programming.
What's A gamma?
A gamma, okay, so here I'm just looking at all, so I have the set of integers, 1 to n. I'm just selecting all m subsets, so, and then A gamma is just the m times n matrix with columns gamma. So that's just the minors. Thanks. Okay, so the first thing that we can have a look at is, maybe before we go to the integer setting, is what do we know for the linear program? So what is if we drop the assumption that we want to have integer solutions, but just continuous solutions? And then things are actually quite well known, at least if we want to have bounds, because now we're actually not looking at anything else than looking at B, which are in the cone spanned by the columns of A. And then we can just use Kara-Theodori, and he'll tell us that we can always find some vector x such that with support less or equal than m, such that A times x star is precisely equal to B. So going back again to the integer setting, if you would like, I'm asking something like I'm looking for equivalent Kara-Theodori type statement just for the integer setting. Okay, so what can we hope for? This bound for the continuous setting is, of course, very nice. We just have an m. Can we expect anything similar for the integer setting? I guess probably it's rather obvious that this will be no. And otherwise, I think most of us would actually have to look for a new job. And there are already like a number of results. So let's start with a very nice and positive case. So if we impose some additional structure on our matrix A, in this setting, if we assume that A, the columns of A actually form a Hilbert basis, so by that I mean that if I look at the semigroup of A is precisely equal to the integer points within the cone of that is spanned by A itself. And if we have this additional structure, there was first a result by Cook, Van Loop, and Scriver, and they showed that in this setting you can always guarantee that you need at most 2m minus 1 elements to generate any element in this semigroup. And then, what is it, 4 years later, Chabot managed to improve this a little bit and brought it down to 2m minus 2. And then I think also for quite a while there was the open question whether one could bring it all the way down to m, so get the equivalent bound as for the continuous setting. And there it was Bruns, Gubledetz, Martin, Henk, or Alexander Martin and Martin Henk, and Robert Weissmuller, they showed that actually you cannot get a better bound than 7/6 times m. So you definitely don't get like the equivalent for the Cavalier-Dori rank, and it's actually still a quite interesting open question where the precise bound is. I've wasted, I think, quite a lot of time trying to improve anything, but I didn't find anything significant. So that's on the positive side. If we want to now go a little bit more general and assume less structure on A, things are going to change a little bit. So there's like the one setting where I just look at the knapsack case, so setting m equals 1. And there, a few years ago, together with Aliev and others, we're able to show that one can just guarantee that the support is less or equal than 1 plus the maximum, the logarithm of the maximum entry of our constraint matrix A. And in the more general setting, where m is not necessarily 1, 2006, there's a nice result by Eisenbrandt and Schmoyen, and they showed that the support is bounded roughly by something like m times the logarithm of the maximum entry of A. And this we were also able to improve a little bit. We were able to show then also in the same paper, 2017, that we can always bound this from above by m plus the logarithm of the determinant of A times A transpose and then the square root of that. I'll briefly show where this term comes from a little later. And also for another purpose that I want to get back later to, I mean, this we can just rewrite with Cauchy-Binet in this way. And if you just want to be able to compare it to the result by Eisenbrandt, you can actually upper bound this bound again just in terms of the maximum entry, if you like. And then we see at least it is a tiny improvement that we got like the m to square root of m. Maybe similar, we can ask ourselves, like for the Hilbert basis case, whether one can actually do a lot better. And we were actually able also to give lower bounds, and we will not be able to reduce the Lorder significantly. So one can actually construct examples where you need at least something like m times the logarithm of the maximum entry to the power of 1 minus some small epsilon. So we'll not be able to improve much, but there's still some gap. And maybe one last note is also that if we want to move on to like an optimization problem, so where we're looking for an optimal sparse solution, it turns actually out that the same bound actually holds. So we can also find an optimal sparse solution that fulfills this inequality. And what I'm going to, one of the things I want to show you today is that actually this kind of freedom that we had to get to the optimal solution, we can actually also use to improve this bound a little bit. And in particular, this will give some nice improvements for the knapsack case. Okay. But maybe just before I go on there, I actually want to go one step backward and just ask the question of finding like a sparse solution for a Diophantine system of linear equations. And surprisingly, to the best of my knowledge, I mean, we haven't been able to find any results in this direction. I mean, even though you would think that everything has been done on Diophantine systems of equations. The only kind of exception that goes a little bit in this direction is, for example, the Siegel types lemma that, for example, look at finding short solutions. I mean, if you want to think of it a little bit, I mean, this sparsity, you can also think of like a semi-norm. So we're also looking to minimize a norm. And that's essentially like the closest that we've seen that comes into this direction. And actually, this is also precisely where this square root of delta determinant of A times A transpose comes from in the previous result. So we've actually employed this result. Okay, so before going on again to the semigroup case, I would like to first just look a little bit at this easier setting where we don't have positivity constraints. And here we can actually give also tight results. And for that, I would just quickly like to introduce some notation. So assume that I have some integer z. I hope we all know that each integer has like a unique prime factorization. And then we can like count various things. And what I want to count is the multiplicities of these prime factorizations. So if I have an z, then the prime omega function is just the function that counts the multiplicities. And then going one step further, we can actually also look at something like what we call the truncated prime omega function, where we just count the multiplicities. And if the multiplicities are too large, we just we cap it by some integer m. And then also immediately, I mean, also from number theory, there's like this little omega function, which just counts the number of different prime factorizations. And just to link it again to the previous results, what we have is, I mean, we have just like this nice chain of inequalities that the little omega function is lesser equal than the truncated omega function, which is lesser equal than the omega function. And clearly, that is then, again, lesser equal than just the logarithm of z. And equality we only have precisely when z is a multiple of like something 2 to the power of something. And what is nice here is a little bit, I mean, so as I said, I mean, the equality only happens like when z is a power of 2. But in average, actually, it is way better. And just using the prime number theorem, one can actually show that. I'm going to hand wave a little bit. The expectation is more of the size log z. And with this notation, what we can actually show for the Diophantine system of equations is that if we first select any kind of non-singular m times m square matrix, then we can always find for any integer right-hand side b some vector x star, such that, of course, a times x star is equal to b. And the support is no larger than m plus the truncated omega, a value of the determinant of delta of our non-singular matrix a tau. Okay. I'll just roughly outline the proof idea. And it is actually quite easy just to show that this statement holds if we just remove the m here. So I'll just focus on that setting because it's easier. So the proof idea here is not overly complicated. And what we actually do is we show a slightly stronger statement, namely that if we have a matrix A, we actually always can find a subselection of columns of A that contain our subset of indices that correspond to tau, and a few more. And in total, we have then just this number of columns. And if we just take this selection, we can guarantee that the lattice that is spanned by this A of gamma is precisely equal to the lattice that is spanned by all elements of A. And by our previous assumption, this would be nothing else than just Zm. And the idea is then just to look a little bit at groups. So what we can do is just look at the quotient group that is defined by the lattice, like Zm, with respect to the lattice that we span by A of tau. And then we know precisely from geometry of numbers that, I mean, the cardinality of this group G tau is precisely just the number of integers within the half-open parallelepiped defined by the parallelepiped of A tau. So if this kind of defines my matrix A, then we see, I think this should be precisely 10 points. So the group is of size 10. And now if we don't span yet the whole lattice Zm, of course there must be some column in A that is not contained in this lattice spanned by A of tau. So we can just take this element, for example, take this like medium-sized dot, and then add it to our selection of columns. And we immediately get that this gives us a subgroup of G of tau. And in particular, we know then that the cardinality of G of gamma, like the new set, must divide G of tau. And with that, we can actually guarantee that the omega function strictly decreases. And then we can just reiterate this process until we cover the whole of Zm, and we're actually done. For this truncated thing, we just need to add a few more extra steps, but I would not want to go into detail here. Okay, so this is, I think, rather nice, and we can actually, I'll get to that in a moment. I mean, it's actually also best possible. But going back again now to our initial problem that we initially were looking at, so where we do have positivity constraints, this immediately gives like a nice, easy corollary just by allowing, like now if we just allow the setting, have the additional assumption that the cone of A actually spans the whole space, then we're more or less in the setting as in the lattice case, and we just have to add like a 2 in front of our m, and we can guarantee that we'll always find actually a positive integer combination of B, where we don't use more than 2m plus the omega m of the determinant value. So that's not too tricky. And maybe just on this part, a few final remarks. I mean, if we get any value for this omega function, we can actually always construct an m times some n matrix, where the n actually depends then on the value that we put here, where we have precisely equality. So we can't do any better here. And then from the proof we've already seen, it is actually rather constructive. So we can actually compute like these relatively sparse solutions. And if we would like to drop this, like from this corollary, this assumption that the cone spans actually Rm, we get like at least the statement that most of the right-hand sides B have a relatively small support, like minimal support. That is just from the fact that if you look at the cone spanned by A, difficulties only arise at the boundary, and if you just exclude the boundary points, you actually can just apply this kind of statement. Okay, so this is actually, I mean, obviously a significant improvement over the bounds that we've seen previously, like for the general settings. And the next question is, can we actually get like proper statements then also for pointed cones, for example? And that will be my next thing I want to look at. And I want to assume now that the cone generated by the columns of A is actually a pointed cone. And if it's a pointed cone, of course, there must be an extreme ray on this cone. And I'm just going to assume that my first column, A1, is actually an extreme ray. And in this setting, we can actually now guarantee that the minimum support of any solution, feasible solution, can always be bounded by m plus 1/2 the logarithm of this sum here. And if you remember, in the previous statement, like in the previous results, we had actually the same result where we just didn't have that the 1 has to be in the gamma. So what we were able to do here is reduce the number of summons by a factor of m over n. Doesn't necessarily need to be any better because, I mean, in theory, all these delta determinants of alpha gamma could be 0. But for general matrices, this is actually an improvement. I don't want to go into detail, actually, of the proof of this, but I want to actually focus on the setting where m is, again, equals to m, because things actually become a lot easier and nicer. So if we assume that m is actually 1, then asking for the cone a1 to an to be pointed is nothing else to either say that all a1 to an are positive or all of them are negative. And extreme rays, we only have 2 extreme rays in the 2-dimensional setting, either the minimum value or the maximum value. And what we can actually do then is reduce things. I mean, also the summand is just a single term then. And we get that if we have a positive vector, A, and we have a feasible knapsack problem, then we can actually say that we find a feasible solution X star where the support is actually 1 plus now the minimum entry of A1 to AM. And that's like an improvement over the maximum entry that we had beforehand. And the proofs of those, I mean, obviously this is a corollary of the theorem, but I can prove the corollary relatively easily. And I'll try to do this. I mean, this is a nice little application of Minkowski. And any application of Minkowski is always a good application, in my opinion. OK, so at its core is this little lemma. So if my t is larger, strictly larger than 1 plus the logarithm of the first entry a1, then if I look at this following system of equations, so I want to have that yi plus ai summing up over those sum up to 0. So it's an element in the kernel of the vector of a1 to at. I want that my vectors yi is non-trivial, so at least one element has to be non-zero. And I want to have that the first element is just positive, and the remaining ones should just be elements -1, 0, or 1. So if we assume that this lemma is true, then deriving the corollary is actually relatively straightforward. So first, we just may assume by reordering that a1 is the minimum element of the numbers a1 to an. And now, instead of looking for the sparsest solution, ax equals b, I'm going to look for the sparsest solution where I minimize the support on x2 to xn. So I'm kind of ignoring for the moment the first variable x1. And then, again, just by reordering, I may assume that the first t elements are all strictly positive, and the remaining entries are 0 from this solution. And now, should it happen that actually t is larger than 1 plus the logarithm of my smallest entry, a1, then I can apply the lemma, and I can just construct k and take this y extended by some zeros and add it to my x, and I can actually strictly decrease the support of x, contradicting this minimal choice. OK. So it just remains to argue why the lemma is true. And here, the idea is actually to apply Minkowski's first theorem. And what I'm going to look at first is these constraints and these constraints, and I'm going to relax them as far as possible. So instead of saying that a1 times yi plus all the way to yt times at is equal to 0, I can just say as well that it is strictly larger than -1 and strictly less than 1. Any integer solution, of course, will then be equal to 0. And similarly, I can relax the integer constraints for the second, for the constraints that I want to be -1, 0, or 1, by just saying that these yi's are supposed to be strictly larger than -2 and strictly less than 2. So I'm going to look at this auxiliary polytope. I can rewrite it a little bit just in terms of the maximum norm, where I define just the matrix of this form. And now it's just an easy volume argument. So we know that Q is just equal to 1 divided by the determinant of m times the volume of the cube with edge length 2. And then with our assumption that t is strictly larger than 1 plus the logarithm of a1, we get that this volume of this polytope is actually strictly larger than 2 to the t. We can apply Minkowski, so there must be a non-trivial integer point in this point. And by our constraints, we know that all the entries of the yi's has to be either -1, 0, or 1. And we only have some freedom for the first variable. But since our Q is actually centrally symmetric, just by flipping the vector, we can always just assume that also the first entry is positive. Okay. And that completes the proof of this little corollary, which I quite like. And
this is not constructive, right? Because you apply.
This is not constructive, no. Unfortunately not. I mean, only in the other setting we're able actually to prove something algorithmically. Obviously, finding sparse solutions is NP-hard, I mean, even for the continuous setting. But even with getting an approximation with this bound is actually, I wouldn't know how immediately, no. But this actually also leads me to my last slide. So you brought it up already. I mean, if we just look at specific right-hand side, B, finding a sparse solution is actually NP-hard. You might be able to find approximations. I actually don't know anything about this. But what we can go actually a step further and define something like, I would call the integer Caradeo-Dori rank of a matrix A. And if we look at all possible right-hand sides B that we get, so it's just A times some positive right-hand side integer vector Z, and I look at the minimal support of those, can we say anything about this term? Can we compute this? And on the positive side, what we can say is actually that if we fix the dimension where the matrix A lives in, so if we fix n, obviously this also will fix then m, then we can actually say that we can compute the integer Caradeo-Dori rank in polynomial time. And what we can do here is just reduce things essentially to counting points and then just using like generating functions. So this is like ongoing work that we're currently on. And as I promised to also pose at least one hardness question, what we weren't able to do is actually prove that computing the integer Caradeo rank is NP-hard. So I would kind of finish my talk with this open question. Thanks.
So how does this relate somehow to this like Frobenius problem, or?
I mean, we do, I mean, this last part, you mean?
Or any of this?
I mean, we do believe there might be some kind of similarities because, I mean, like the behavior is quite similar. I mean, we can formulate things in this Pressburger arithmetic, like for all k there exists, or like from something onwards. But I mean, the support itself, I'm not aware that there is any direct connection to Frobenius problems.
Okay.
Sorry.
And what do you? So what exactly do you use to try and compute this?
So what we can actually do here is, I mean, like on a high level, what we can just do is, if we want to look whether we can actually represent every element in the semigroup by k elements, what you can just do is look at all subselections and choose k, produce like count all those cones, add them together, and then just see whether you can actually cover everything. So in this generating functions, I mean, you can easily do like disjunctions, intersections, and complements.
I see.
So that's the idea behind that.
I see. But so it doesn't like reduce black box to some sort of like Barvanok algorithm. It's like you have, you have to like work.
A little bit. You have to work a little bit.
Yeah, so I don't remember the exact result, but if you're willing to go to 2 to the n, isn't there some kind of integer cross-difference there on that?
You mean this one here?
Yeah. Suppose I'm willing to pay 2 raised to the power n.
Yeah, yeah.
instead of 2m, right?
Yes.
Is there a theorem, I forget the exact term, but is there a term that says, there's some Carothea-Razak theorem, which says you can express anybody in the convex hull of a bunch of integer points as a convex combination of just 2 to the n mod n.
Yeah, with his parity arguments then.
Yeah, with the parity of.
Yes, yeah.
But you're not happy with 2 to the m, obviously.
No.